Today we're going to look at the inverse normal distribution function, which is also known as percentage points. What this is if we know that we've got something that can be modelled as a normal distribution and we know the mean and standard deviation of that normal distribution, then if we know the probability that a value is less than a certain number, then we can work out what that number is. So to put that into a bit of algebra, if we know the probability is P, that x is less than a, so that our variables are less than a value, then our calculator will tell us what that value a is. So let's look at some examples of this. And it's asking us to draw diagrams to ensure our answer is correct, but I would be drawing a bell-shaped curve for these questions anyway to help me out. So for question A, with our normal distribution function with a mean of 20 and a standard deviation of 3, we want to know what value has a probability of x being less than the value of 0.75. So using our calculators, we're going to go into mode 7 for the distribution mode, and there is an option for the inverse normal. So we're going to set our area as 0.75, our sigma first is standard deviation of 3, and our mean of 20. And that will tell me that the value that has that probability is 22.0. So my A is 22.0. So the probability of x being less than 22.0 is 0.75. Let's check that this makes sense using our bell-shaped curve. And we know that our mean is 20. So if we're looking at something more than 20, like 22.0, our probability of being less than that value is going to be greater than 0.75. Greater than 0.5, so 0.75 makes sense. So we've checked by drawing a diagram. For part B, we want the probability that x is greater than a value to be 0.4. Now we don't have a function for that on our calculator. The inverse function tells us the probability that x is less than a value. Well, drawing our bell-shaped curve, if our probability that it's greater than a value is 0.4, that means it's to the right of the mean, so to the right of the value of 20, so the probability of being greater than it is 0.4. Well, that means the probability of being less than it is 0.6. Since our probabilities add up to a whole one. So the probability of x being less than a is 0.6, and now we can use our calculators. So this time we want the area to be 0.6, we're keeping the same standard deviation and the same mean, so our value is 20.8 to one decimal place. So that makes sense because we could see it was going to be greater than 20, and we knew it was going to be less than 22 because that was what gave us a probability of 0.75, so we wanted something smaller than that. For part C, it's starting to get a bit trickier. We want the probability of being between 16 and A to be 0.3. So if I draw my curve, I can't be entirely sure whether A is bigger than the mean or not, but I know that being between 16 and A has a probability of 0.3. Now if I work out the probability of being less than 16, I will then be able to add these two probabilities together and get the probability of being less than A. So the probability that x is less than 16, I can work out using my normal distribution. So this time I need to go back into the distribution function as option 7 on the menu and use my normal cumulative distribution. So my lower value is something very small. So let's use minus 9 times 10 to the 99. And my upper value is 16. And I'm using let's check that I've got my standard deviation is 3 and my mean is 20. So my probability here is 0.0912. So this little probability here, 0.0912. So my probability that x is less than a is these two added together. So 0.3912. So now I can use my inverse function. And my area needs to be 0.39121. My standard deviation and my mean are already in correctly. So my value of A is 19.2 to 1 decimal place. So let's look at a similar situation where we're looking for a probability in a range, this time from A to 24. And I want that probability to be 0.42. So if I sketch my curve, I want to be between 24 and my value A. I don't know whether that will be above or below my mean, so I'll just sketch it in for now. And I want this probability to be 0.42. Now I can't work out my value of A straight away, but what I can do is use my probability of x being less than 24. So if I can calculate that on my calculator, so using the normal cumulative distribution again, using a really small lower value, an upper value of 24, and my standard deviation needs to be 3 and my mean 20. So that gives me 0.90879. So that means my probability that x is less than a is that value take away 0.42. So I can do that calculation using option 1 of my calculator. I want my answer, take away 0.42, and that gives me 0.48879. So now I know my probability that x is less than a. I can use my inverse function. So back into option 7 and the inverse normal. My area is 0.48879. My standard deviation is still 3 and my mean is still 20, and that gives me a value of A of 19.9 to 1 decimal place. So the thing to remember is what the inverse normal distribution gives you is the value for which the probability of x being less than that number is the probability that you're using. So if you want to find the value that has a probability of being greater, then you need to do 1 minus the probability. And if you're using a range, then these diagrams start to come in really, really handy. Let's have a look at a couple more examples. So example 2, we've got plates made using a manufacturing process, and the plates have a diameter d centimetres, and we know that the diameters are distributed using a normal distribution with a mean of 20 and a variance of 2.25. So that means sigma squared is 2.25, which gives us a sigma of 1.5. Remember to use the square root of this number as your standard deviation. In part A, we've been told that 60% of the plates are less than x centimetres. So that means the probability that D is less than x is 0.6 or 60%. So we can type that problem straight into our calculator. using the inverse normal. So our area is 0.6, our standard deviation is 1.5, and our mean is 20. So we get a value of x as 20.38. Let's check this makes sense using a bell-shaped curve. So we know our mean this time is 20. So we would be expecting a value greater than 20 to give us a probability of 0.6, because anything less than 20 would have a probability of less than 0.5. Part B, to find the interquartile range. Remember, the interquartile range is the upper quartile take away the lower quartile, and to get your upper quartile you need to be looking at a probability of being less than it of 0.75, and to get your lower quartile the probability of being less than it is 0.25. So we want an upper value such that our probability D is less than that upper quartile is 0.75. So using our calculator, inverse normal function, area 0.75, we've already got the right standard deviation and the right mean, so we get 21.01 for our upper quartile. For our lower quartile, we want a probability that D is less than that value of 0.25. So on our calculators, exactly the same calculation as before, but with the probability of 0.25, and that gives us a value of 18.99. So that is our lower quartile. So our interquartile range is the difference between them. So option 1, so that we can perform the calculation, gives us 2.02 as our interquartile range. Okay, let's have a look at example 3. This time we're looking at the wingspans of a population of birds with a normal distribution, and the birds have a mean wingspan of 14.1 and a standard deviation of 1.7. So let's write this using the notation that we're used to seeing. So let's have x be the wingspans in centimetres. So x, it has a normal distribution with a mean of 14.1 and a variance of 1.7 squared. So in part A, where we want the wingspans to exceed 90, the wingspan which will exceed 90% of the population, we want the probability that x is greater than a value to be 0.1, 10%, or the probability that x is less than the value to be 0.9, whichever way you want to think about it. This is the one that we use to type into our calculator though. So back into our distribution function, inverse normal, area 0.9, standard deviation 1.7, mean 14.1, and that gives us our value of 16.28 centimetres. Let's check this makes sense. Our mean is 14.1, so we're looking for something bigger than that to give us a probability of 0.9. If we want the wingspan to exceed 20% of the population, we want the probability x is less than a to be 0.2. So this time, if we're wanting a small probability, we're wanting a number a bit below 14.1. So let's just change our calculation to have that probability of 0.2, and we get 12.67. So that is substantially lower than the 14.1 mean. And then if we want the limits of the central 95% of the wingspans, so that would mean we want the area in the middle to be 0.95, which means we want 2.5% at either end. So we want this to be 0.025 and this to be 0.025. So if I call these values A and B, then the probability that X is less than B is 97.5%. So on my calculator I can work out that value of B. And it's 17.43. And then I can work out my value of A, because my probability that X is less than A needs to be 2.5%. So that gives me a value of A of 10.77. So the limits of the central 95% of the wingspans are those values there. And that's the inverse normal distribution function. So your turn to have a go. There's a worksheet to have a go at. I'm going to put the answers on Show My Homework as well, so that you can mark your own work and then just let me know how you've got on.